In our next video, we'll continue with Chapter 12 and we'll discuss surface tension, vapor pressure, and viscosity. Surface tension is a property of liquids whereby the network being limited at the surface leads to stronger interactions at the surface of a liquid. It's the reason that liquids form spherical drops, because the interactions being stronger at the surface lead to these cohesive forces forming similar to spherical drops by having a net pull from the surface to the interior of the liquid. This is what allows objects that are even more dense than water to float on water, because water has a high surface tension. So the surface tension of water at room temperature is 72.8 millijoules per square meter, whereas the surface tension of a nonpolar substance like benzene is much lower because it doesn't exhibit hydrogen bonding. Benzene is only 28 millijoules per square meter for the surface tension. You can see here that the surface tension of molecules it results from, for example, molecules can only interact with what's shown here, 4 neighbors at the surface, whereas the interior molecules can interact with more neighboring molecules. This leads to a stronger network of interactions at the surface because these intermolecular interactions are only being shared by fewer molecules. The stronger these intermolecular interactions are, the higher the surface tension will be. As we saw earlier, polar molecules like water, which water in fact exhibits hydrogen bonding, is going to have stronger surface tension than a molecule like benzene, having only carbon and hydrogen bonds and lacking hydrogen bonding. Additionally, raising the temperature of the liquid reduces its surface tension because the average kinetic energy of the molecules at the surface is higher, and this increased molecular motion makes it easier to stretch the surface and reduce those intermolecular interactions. The next topic we'll discuss is viscosity. Viscosity is similar to surface tension in that it depends on the intermolecular interactions. Viscosity is defined as the resistance of a liquid to flow. So we can measure viscosity in units of poise, which is 1 gram per centimeter per second. Often the units are given in centipoise, and water has a viscosity of 1 centipoise at room temperature. Larger intermolecular interactions are going to lead to a higher viscosity. For example, we saw that the hydrocarbon chain length, as it increases, the boiling point increases. Well, similarly, viscosity will also increase with hydrocarbon chain length. Here we have pentane versus hexane versus heptane versus octane versus nonane, and this actually is from 5 carbons versus 6 carbons versus 7 carbons versus heptane has 7, and then octane has 8, nonane has 9. You can see that the viscosity here is given in centipoise, and it increases from 0.24 to 0.36 to 0.41 to 0.54 to 0.71 as we increase from 5 carbons to 9 carbons. So larger intermolecular interactions will lead to higher viscosity. And this is demonstrated by, for example, motor oil. If you've ever poured motor oil, you know it has a higher viscosity than something like water. And this is because it has longer chain length, and it's going to have larger intermolecular interactions. The Society of Automotive Engineers, or SAE uses this SAE viscosity scale to measure the viscosity of motor oil. This SAE scale goes from 0 to 60, and the W that you see on the front of your motor oil stands for winter. So, for example, a 5W30 motor oil means that the SAE viscosity is 5 in the winter and 30 in the summer. This is due to these motor oils being designed such that the molecules will roll up in the winter when the viscosity is meant to be smaller, and stretch out in the summer when a higher viscosity is necessary in order to lubricate the engine. In years past, before these newer modern motor oils were developed, automotive owners would have to change out their motor oil for a summer oil versus a winter oil. But now the motor oil can be left in all year because these newer motor oils are designed to respond to temperature changes by rolling up to decrease the viscosity and spreading out to increase the viscosity. Here we can see that the viscosity is affected by temperature. For a substance that has a viscosity of 1 centipoise at 20 degrees C, for example, something like water, the viscosity lowers at 40 to 0.6, at 60 to 0.7, at 80 to 0.3, and at 100 to 0.2. So viscosity decreases as the temperature increases, and this is because it's easier to overcome the intermolecular interactions at higher temperature. The next topic we'll discuss is capillary action. Capillary action is the ability of a liquid to flow up a thin tube against the influence of gravity. We're going to see an example that demonstrates the narrower the tube, the higher the liquid rises. And this is because capillary action is the result of two forces working in conjunction with each other, cohesive forces holding the liquid molecules together, and adhesive forces attracting those molecules to the surface of the tube. You've probably experienced this if you've had a blood test that used a capillary tube to store the sample for later processing. We see here some examples of capillary tubes having different radii. So the capillary tubes with the smaller radius is going to have the higher the column of liquid. And this is because the adhesive forces inside the tube are able to draw the liquid further up against the pull of gravity than those in the larger tube. You see here that water is attracted to the sides of a tube, whereas a substance like mercury that is nonpolar is going to be slightly repelled by glass. So the water is actually attracted to glass, and if you're measuring water inside, say, a graduated cylinder, or if you're storing water in a test tube, you've probably noticed this meniscus where the water is concave slightly, and the sides of the water is actually attracted to the tube a little bit, causing this concave effect due to the adhesion of the water to the glass. Mercury forms a convex meniscus in a glass tube, and that is because it's actually slightly repelled by the glass, and the cohesive forces are stronger than the adhesive forces to the glass. Molecules in a liquid are in constant motion. The average kinetic energy of these molecules is proportional to their temperature. But even at a specific temperature, some molecules have more kinetic energy than others. So the molecules that have higher kinetic energy if they're near the surface of the liquid, they may be able to overcome the attractive forces at the surface and enter the vapor state. The larger the surface area of a liquid in a container, the faster the rate of vaporization, because the more of these high energy molecules will be able to reach the surface and enter the vapor state. We see here a distribution of thermal energy demonstrating that at a specific temperature, some molecules will have higher kinetic energy than others. Only a certain number of molecules, a small percentage, will have enough energy to enter the vapor state, overcoming the adhesive forces or the cohesive forces holding these molecules together at the surface. But the higher the temperature, the more molecules will have that can enter the vapor state, and the faster the rate of evaporation. Condensation is the process whereby molecules that are in the vapor state will lose enough energy through molecular collisions to re-enter the liquid state. Some of them may even form droplets on the surrounding surfaces and run down the sides of the surface. We call this process condensation. Vaporization and condensation are opposite processes. In an open container, vapor molecules can generally spread out faster than they condense, because they aren't trapped by the container. The net result of this is that the rate of vaporization is greater than the rate of condensation, and we have a net loss of liquid. But in a closed container, the vapor can't continue to spread out indefinitely, and the result is that in a closed container, the rates of vaporization and condensation equalize over time. Liquids that evaporate easily are said to be volatile, and liquids that do not evaporate easily are said to be non-volatile. So if liquids have weaker attractive forces, they'll be more volatile and have a faster rate of vaporization. If liquid molecules have stronger attractive forces, they will have a slower rate of evaporation. So the rate of evaporation increases with increasing temperature and also with increasing surface area, and decreases with decreasing temperature and decreasing surface area. So the rate of vaporization increases also with decreasing strength of intermolecular forces. Which of these samples of water has the greatest rate of evaporation? We see that they're all 100 milliliter samples. 2 of them are at 25 degrees C and 2 are at 55. So we can assume that the higher temperature sample would have a higher rate of vaporization. One of them is in a 250 milliliter container and the other is in a 100 milliliter container. The 250 milliliter container would have a larger surface area and therefore would have a greater rate of vaporization. And we see that here, that the higher temperature sample in the larger container has a larger rate of vaporization. When high energy molecules are lost from a liquid, it lowers the average kinetic energy of the system. If that energy is not regained by the liquid, then the temperature actually decreases from the process of vaporization. Therefore, we see that vaporization is an endothermic process. Since vaporization is the opposite of condensation, condensation is an exothermic process. You've probably observed this if you've stood under a cooling fan, maybe at an amusement park in the summer, that is spraying water. The evaporation of the water actually lowers the temperature around that cooling fan, and that allows the park attendees to cool down. So vaporization requires the input of energy to overcome the attractive forces of molecules, and so these molecules when they overcome those forces, are taking that energy along with them, lowering the temperature of the system that's left behind. We call the amount of energy required to vaporize 1 mole of a liquid that liquid's heat of vaporization, and we abbreviate that as delta H of vaporization. Sometimes it's called the enthalpy of vaporization. It's always endothermic because vaporization takes energy, and it's going to have a positive delta H. It is a little bit temperature dependent, and we're going to see that in this chart. The delta H of condensation is exactly equal and opposite the delta H of vaporization. So if you know one, you can use that to calculate the other. So water has the chemical formula H2O, normal boiling point of 100, and a delta H of vaporization at the boiling point of 40.7 kilojoules per mole. Water isn't as temperature dependent, and it also has a delta H of vaporization at 25 degrees C of 40.7 kilojoules per mole. For isopropyl alcohol, we have the formula C3H8O, normal boiling point of 82.3 degrees C. At that boiling point, the delta H of vaporization is 39.9 kilojoules per mole, and at 25 degrees C, we have a 45.4 kilojoules per mole delta H of vaporization. For acetone, those values are 29.1 and 31. For diethyl ether, those values are 26.5 and 27.1. So you see here that the hydrogen bonding effect of water, since it has essentially 2 hydrogen bonds per molecule, is greater than the hydrogen bonding effect of isopropyl alcohol because it only has 1 OH bond. And then we have weaker intermolecular interactions in acetone and diethyl ether. These are polar, but they don't have hydrogen bonding, and you can see it takes less energy to vaporize those at the boiling point and at 25 degrees C, which is room temperature. In a closed container, we can reach what's called dynamic equilibrium when the rate of vaporization and condensation of a liquid are equal. So the total amount of vapor doesn't change. The evaporation and condensation effects are still occurring, but these are opposite processes, and they reach a point where there's no net gain or loss of either the vapor or the liquid, and the rate of evaporation is equal to the rate of condensation. This is called dynamic equilibrium. We're going to be viewing equilibrium a lot in this class, and this is just our first example of it. So we can see here on the left, the liquid, we stopper a beaker that has, or a flask that has water in it, and there's essentially no vapor. Then the water begins to enter the vapor phase, but the stopper is there to keep the evaporation from continuing into the atmosphere, and eventually the vapor begins to recondense and reform the liquid, and at some point we reach an equilibrium where the rate of evaporation is equal to the rate of condensation. We see here a plot of the rate of evaporation, which is fairly constant in this system, and the rate of condensation begins to increase until there's no net change in the two, and at that point we've reached a dynamic equilibrium. So again, it doesn't mean that there are equal amounts of vapor and liquid. It means they're changing by equal amounts. Vapor pressure is the pressure exerted by a vapor when it's in this dynamic equilibrium state. The weaker the attractive forces of a liquid, the higher the vapor pressure will be, and the more volatile the liquid is. So if we increase the volume of a chamber, it'll decrease the vapor pressure inside the chamber temporarily until that equilibrium is reestablished. We see that demonstrated here. We have dynamic equilibrium in a container with a piston. We've reached dynamic equilibrium, But if we increase the volume of the container by pulling up on the piston, then the vapor pressure falls until dynamic equilibrium is restored. If the volume is decreased, the pressure will rise, more gas will be condensed, and the pressure will be greater until the dynamic equilibrium is restored. In the end, when all of these systems reach dynamic equilibrium, the vapor pressure will be the same in each. The system in dynamic equilibrium can respond to these changes, but it takes a bit of time. But over time, the system responds to minimize the disturbance and return to a state of equilibrium. Like we mentioned earlier, vapor pressure and evaporation is dependent on temperature. As the temperature increases, the vapor pressure also increases. We see here a vapor pressure curve where we have the boiling point demonstrated at normal atmospheric pressure as a line here. And we see 4 different substances: diethyl ether, ethyl alcohol, water, and ethylene glycol. The diethyl ether, we see that as we increase the temperature, the vapor pressure increases. There are weaker intermolecular interactions here, and we have a normal boiling point of 34.6 degrees C. For ethyl alcohol, the intermolecular interactions are slightly stronger, but we still observe a temperature-dependent increase in vapor pressure versus temperature. We have a normal boiling point of 78.3 degrees C. For the water, we observe a similar effect where we have a boiling point of 100 degrees C, but ethylene glycol has even higher vapor pressure, higher intermolecular interactions leading to a lower vapor pressure, and the ethylene glycol then doesn't have as high a vapor pressure versus change in temperature. The boiling point is defined as when the temperature of a liquid reaches the point where its vapor pressure equals the external pressure. At this point, bubbles can form anywhere in the liquid, and the evaporation doesn't just occur at the surface. It occurs all over the entire liquid. We call this phenomenon boiling. The boiling point can vary according to the external pressure, which is the atmospheric pressure. So the approximate pressure at higher elevations is lower than at sea level. At sea level, the normal atmospheric pressure is 1 atmosphere. In Denver, Colorado, it's 0.83, and we see the boiling point change from 100 at 1 atmosphere to 94 at 0.83. At a higher state, our higher elevation, we have a pressure of 0.6 atmospheres and a boiling point of 87 degrees C. In Denali, Alaska, we have an approximate pressure of 0.46 atmospheres and a boiling point of 83 degrees C. And on the highest mountain peak on Earth, in Tibet, on Mount Everest, we have an approximate pressure of 0.32 atmospheres and a boiling point of 78 degrees C. And this is why it takes longer to boil maybe noodles at these higher elevations, and why if you're doing some canning, you would need to use a higher weight at those higher elevations. So you would use a higher weight to increase the pressure and to therefore increase the boiling point, respectively.